Okay, we're back. Let us very quickly summarize where we left off and what our task is. We talked about the fact that to find the probability that any one of our systems in the ensemble upon observation is found to be in microstate J, that probability is going to be the number of systems in the ensemble that happen to be in microstate J when the dominant distribution is obtained, divided by the total number of systems in the ensemble. And so there are omega star ways of achieving the dominant distribution such that omega star is so much larger than all the other statistical weights for all the other distributions so as to dwarf them and make them insignificant compared to omega star. And so once we identify omega star, we will be able to form this expression. And so the question is now, how do we find the dominant distribution? Said another way, how do we find the set of numbers n1 star, n2 star, n3 star, number of systems in the ensemble in microstate 1 when the dominant distribution is obtained or observed, number of systems in the ensemble in microstate 2 when the dominant distribution is observed, and so on. How do we find this distribution, this set of numbers? If this dominant distribution truly has the maximal omega, it has the largest omegas, the largest statistical weight, then in principle, we ought to maximize omega. We have to find the values of n1, n2, n3, and so on through all the microstates for which, that is to say, the distribution for which omega is a maximum. Omega, the statistical weight, is a multivariable function of these variables, n1, n2, n3, and n4. But the variables themselves are not entirely independent. First of all, we know that n1 plus n2 plus n3 and so on, when we add up all the systems in the ensemble in microstate 1, plus all the systems in the ensemble in microstate 2, plus all the systems in the ensemble that happen to be microstate 3 for the distribution, and do this for every microstate, when we add them all up, we have to get the total number of systems in the ensemble. The ensemble systems are all distributed among their microstates. If we look over all of them and add them up, we have the total number. So we have to find the maximum value of omega. And remember, in single variable calculus, let me remind you again, we mentioned this in our Zoom meeting just recently, that when you're maximizing a function of a single variable, you're setting its derivative equal to 0. So you're finding the derivative, setting it equal to 0, and finding for which values of the independent variables is the derivative of the dependent variable of the function 0. For a multivariable function that depends on many variables at once, to maximize or to find an extremum of a function of many variables, you have to find the derivatives with respect to all the variables and set them equal to 0. But we have a slightly different circumstance. The circumstance that we are in is not just maximizing omega for any possible values of n1, n2, n3, and so on. We're maximizing omega subject to constraints. There are two constraints. The first constraint is this, that these are not all random variables. When you add them all up, they have to sum to pi. And so first, number one, we are finding the maximum value of omega as a function of these variables, but only such that the variable values have to add to pi. That's condition number one. There's actually another condition, and another condition is that the total energy of the ensemble is fixed. For ensemble as a whole is constant or fixed. And this constant total energy can also be related to the systems in the ensemble in all the different microstates for this distribution by summing over the microstate J n sub j times E sub j. When each system in the ensemble, when a specific system in the ensemble has microstate J, it will be described by some many-body wave function. It will also have associated with it a specific energy eigenvalue, E sub j. Now, the energies might be degenerate, but nevertheless, to each unique microstate of a macroscopic system, there is associated an energy eigenvalue. Maybe not unique, might occur many times. This is the microstate index. Microstate of system with NVT. So when we look at how many systems we have in microstate 1, we multiply that number of systems by the energy of microstate 1. That's the total energy of all systems in microstate 1. Then we look at microstate 2. The energy value of that microstate 2 will be something. Maybe it's the same, maybe it's not. But then there will be the total energy of all the systems in microstate 2. We would multiply N2 by E sub 2. We would add it to the first. And when we do this, at the end, we will find the total amount of fixed energy that our ensemble has trapped in it by virtue of the adiabatic walls. Rigid adiabatic walls. And so we have two constraints. We have to maximize omega subject to constraint number 1, that the sum of all the variables has to add up to pi. They're not completely independent. And that the total energy of the ensemble is also constant. So when I multiply the energy eigenvalues for each specific microstate by the number of systems in the ensemble in that microstate and add them all up, I get a constant. And so we are finding what's called a constrained extremum. Must find constrained extremum of omega of n1, n2, and so on. We are finding that distribution, that set of numbers, n1, n2, n3, n4, and so on, for which omega is an extremum. Specifically, we are looking for a maximum, subject to this constraint and that constraint. And the way to find a constraint maximum is provided by something called the undetermined Lagrange multiplier method. We've mentioned it already in class before. I refer you to the back of Hill's book. There's also something in Engel and Reed about it. There's also something in Ralph Bayerlein's book about it, actually something quite good. And so our approach is to use the method of Lagrange undetermined multipliers. We're not going to derive the method or the technique from the very beginning. There are many resources that do an excellent job of doing so. We're simply going to use it. So I refer you to those resources or calculus books or any other resource on Lagrange undetermined multipliers that you may want to find that makes most sense to you. What the procedure, the algorithm entails of this method is as follows. That we will just effectively use. That instead of maximizing omega, to find the constrained maximum of omega is the same as finding the unconstrained maximum of a different function. the unconstrained maximum of the following function. Actually, let me say one more thing before we go on to find this unconstrained, or this constrained maximum of omega. Remember that omega, so the distribution will look something like N1 systems in microstate 1, N2 in microstate 2, N3 in microstate 3, and so on. Omega, remember, is the total number of systems in the ensemble divided by N1 factorial, N2 factorial, N3 factorial, N4 factorial, and so on. This is the total number of systems in the ensemble pi factorial. Remember that pi is also equal to sum on all j from 1 to infinity of n sub j. When you add up all of the n's in the denominator, you should get pi. And so we talked about the fact that when pi goes to infinity, omega is a very, 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 very sharp function. It is highly, highly peaked for the specific distribution that we've called the dominant distribution. Very, very sharp function. It is more desirable or more, more I guess advantageous or convenient to maximize not omega itself, given how sharp of a function it is, but to maximize the logarithm of omega. And that might seem strange. And so what we will ultimately do is find the extremum. Oops, I can't even read that. Find the extremum not of omega, but of the logarithm of omega. Two things I want to say. Number one, I will, in this class, be using the symbol log for the natural logarithm instead of ln. I'm just used to doing that. It's kind of more natural to me. The natural logarithm is the only logarithm that you will effectively encounter in this class. So when I write log, you may interpret that as ln. It's now bred into me. I can't do it any other way. So it's always going to be the natural log. Number two, the logarithm of a function is a much more slowly varying function than omega itself. So the logarithm of omega, which depends on n1, n2, n3, n4, and so on, omega itself is a very, very sharply peaked function as a function of these variables. The logarithm of omega is a much less sharply peaked function. The logarithm of omega kind of tends to spread out a function in a sense that used to be very highly peaked, or that'll be a consequence thereof. And so it is more convenient to maximize log omega from that perspective. Are we sacrificing anything in doing that? We're not. Because the logarithm of omega is a monotonic function of omega. The larger the omega, the larger the logarithm of the omega. And so when you maximize omega, you also simultaneously maximize the logarithm of omega. Or when you maximize the logarithm of omega with respect to these variables, you simultaneously also maximize omega itself for the same set of variables. And so one can use that interchangeably, but because this is such a sharp function, we would like to make it more smooth or well-behaved and maximize the log of omega without sacrificing anything. There's another reason, actually, and arguably more important reason as to why we would want to use the log of omega and work with that as opposed to omega itself. And that is because of these factorials. These factorials are generally kind of complicated to deal with, and are kind of very rapidly changing functions. And there exists a formula that you are going to derive on your homework on your problem set 3 that relates the logarithm of a number factorial to something that is a bit more manageable. That approximation is called the Stirling approximation. So the Stirling approximation, or Stirling's approximation, is that if you have a logarithm of some number n factorial, this is approximately equal to n times the logarithm of n minus n, when you take the limit as n goes to infinity. This becomes an equality. It is no longer an approximation. And so this is known as Stirling's approximation. And anytime you see a logarithm of a number factorial, you can undo the factorial or get rid of the factorial by writing it as n times log n minus n. That's the formula, and that's what you're going to derive. And so this formula becomes exact, this approximation becomes exact, and the limit as n goes to infinity. We are working in that limit. And so it's particularly straightforward for us to use this and to then be maximizing or finding the extremum of a logarithm, not of some crazy factorials, but of a function that is a bit more manageable. And so that's what we're going to do, and that's what you're going to prove on the homework. So here's what we're doing ultimately. The method of Lagrange multipliers says this. We would like to maximize or find the extremum value of the logarithm of omega, as it depends on n1, n2, n3. We are finding the maximum value of the statistical weight, of the logarithm of the statistical weight. To use the method of Lagrange multipliers, use Lagrange's method to find constrained extremum of the logarithm of omega. To do this, form a new function. Form a new function. Let's call it big L, where this new function is going to be log omega minus the first Lagrange undetermined multiplier, a constant for us to determine, multiplied by the first constraint, and I'm going to use the index, I'm going to use the index I, ni. This is from 1 to infinity. I'm going to write this down, and then we're going to, again, emphasize this, minus the second Lagrange multiplier that we're going to call beta, another constant as far as we're concerned, times the second constraint. The second constraint is the sum of number of systems in microstate I in this case, or microstate J, doesn't matter. In my notes I wrote I guess I've been lying you with J, so I'm just going to randomly switch to I, and I hope you don't hate me for it. The number of systems in microstate I times the energy eigenvalue of that microstate when it's in microstate I. This is the function that we're going to maximize. Alpha and beta are known as the Lagrange undetermined multipliers, to be determined. And the idea is that to find the constrained extremum of this function, that is equivalent mathematically to finding the unconstrained extremum of this new function, where this new function L for Lagrange is the original function that we were trying to find the constrained extremum of, minus an unknown constant as of yet, times the first constraint, minus a second unknown constant times the second constraint. Just a very quick aside, just say, this, our constraint looked like this. For the second constraint, for example. And the first one looked like a sum over ni is equal to pi. The common way to do this is to subtract E total from both sides in here, and then that's what beta should be multiplying. What we'll find is that it doesn't really matter. We can go on and write it like this, not like this that you might have seen when you find standard derivations of the Lagrange multiplier method. Because what we're about to go on to do is to start taking derivatives with respect to variables. And when we take a derivative of E total with respect to any variable, given that it's a constant, it's going to be 0. And so we're not making a mistake. And so once again, to say this, to find the constrained maximum of log omega is the same as to find the unconstrained maximum of L, where L is log omega, the function we wanted to constrain and maximize, minus constants multiplying each constraint, a different multiplier for each constraint that our maximization was subject to, or extremization. What does it mean to find the unconstrained maximum of this function L? Well, just like we just talked about a second ago, to find the unconstrained maximum of a function of multiple variables, the variables are n1, n2, n3, n4, and 5, and so on, is to find all of its derivatives with respect to every possible variable, all the ni's, and set them equal to 0. And if you do that for this new modified function, you will then obtain the set of numbers n1, n2, n3, n4, and so on that correspond to the constrained maximum of this function log omega subject to these two constraints. So that's what we're doing. We have formed this new function. Now we're going to find its unconstrained extremum. To find its unconstrained extremum, we take its derivatives. Derivatives with respect to what? With respect to the variables on which this and this new function depend on. The set of n1, n2, n3, and so on. So instead of a function of just x, we have a function of x, y, z, omega, m, and so on. We have a multivariable function where there are many variables on which the function depends. And so that's what we're about to do. And so let's attempt not to whack anything as I whack something. And so once again, we are maximizing or finding the extremum of this new modified function. And so to find unconstrained maximum of this new function L, which is log omega, n1, n2, and so on, minus alpha sum on I, ni, minus beta sum on I, ni, ei. To find the unconstrained maximum of this function, we have to set the partial derivatives of this L with respect to ni to 0 for all I equals 1, 2, and so on. And so we have to take the derivative with respect to of this function with respect to all the ni's. Let's do this for the general ni. We're going to do this for some ni. So we're keeping I general. We're going to take the derivative of L with respect to some specific ni. Before we do that, though, let's help our case. Let us use the Stirling approximation. Remember that omega is a crazy function with all these factorials. But log of a function with factorials can be simplified through Stirling's approximation. So let's do that. Let's simplify log of omega through Stirling's approximation. So first, Stirling. So log of omega is log of pi factorial over n1 factorial, n2 factorial, and so on. This is also equal to log of, in the numerator, pi can be replaced by a sum over all I of ni. We've now seen this. Whole thing factorial divided by n1 factorial, n2 factorial, n3 factorial, and so on. Now we're going to use a log rule. Before we even use Stirling, we're going to use a log rule because log of a ratio of two numbers, this number and that number, is the difference between the logs. And so this thing is going to look like log of the numerator minus the log of n1 factorial minus the log of n2 factorial, and so on, minus all of them. And now we're going to apply Stirling's approximation. I'm going to try to get down and write Stirling below. Actually, you know what? That's probably a dangerous proposition. I'm going to go back to the top. So this was not Stirling yet. I apologize. This was simply log rules. I won't even write anything down. So this is just decomposing what this is. This is how we can also write it without sacrificing anything. Now apply Stirling's approximation. Stirling. The first term is log of this scary looking sum, ni, whole thing factorial. We'll think of this thing inside the parentheses as a single quantity. Now we apply Stirling's approximation. This is going to look like, remember it was log of n factorial was n log n minus n. So log of the thing inside the parentheses factorial is thing in parentheses, log of thing in parentheses, minus thing in parentheses. So this should look like ni times log of sum over ni. Notice the factorials are all gone now. Minus sum on I and I. Similarly for the other guys, looks a little bit easier. Log of n1 factorial is n1 times log of n1 minus n1. Log of n2 factorial is n2 log of n2 minus n2, and so on. So this is Stirling's approximation applied to all of them. So now we can put it all together. We can say that log of omega is equal to, having applied the Stirling approximation, Stirling applied to each of these guys, log of the sum over ni's minus the sum over ni. Now, minus n1 log n1, and now plus n1, minus n2 log n2, and plus n2, and so on for all of them. I can group all of these guys together. I can put all of these guys together into a single sum, and that single sum is going to look like, make sure I get that right, sum on I, ni log ni, right, for each of these guys. I'm sorry, for each of these guys, log ni times log ni for all I. But now, instead of minus n1, because we are subtracting here, this sign gets flipped. So plus sum on ni. This term is going to cancel that term. So we're going to be left with this and that. And that's what log omega looks like after we apply Stirling's approximation to it sequentially. It still looks a little bit daunting, but at least the factorials are gone, and that's going to be a little bit more comfortable to deal with. And so that's the function that we obtain. It's this minus that sum. These peripheral terms are now gone, having canceled each other. And so now we find the derivative. We now take the derivative of this quantity log omega minus the two constraints, and then we differentiate what we get in the end and set that equal to 0. So let's do that. Let me not erase here. Maybe I'll need to come back to it, but maybe not. We'll see. Let's erase what's on the other side. Okay. So we have aided our case by sequentially applying Stirling's approximation to this Lagrange function L that we're going to find the unconstrained extremum of. And so let's do this. Our function, once again, L now looks like sum on I, ni times log of sum on I, ni minus sum on I, ni log ni. Now minus the two constraints. Minus alpha sum on I, ni minus beta sum on I, ni e sub I. That's the function that we must now take a derivative with respect to. So we are finding dl, d, and let's say dn with respect to a specific value of I. Let's say it's, because we've been using here I as a generic summation index, let's say we're taking the derivative with respect to L, taking the derivative of L with respect to some specific n. Suppose it's n sub k. Maybe it's n57. Taking the derivative of the function L with respect to the number of systems in the ensemble in microstate 57, or microstate k. This is what we're doing. And so we're taking this derivative, and so that's what we're going to do. Let's do it. Let's do this piece by piece. Let's first take the derivative of log of omega. So we want d, and k first of log of omega. This, right, this is log of omega. We'll deal with the other terms second. Right, the derivative of all of these terms, the derivative of the entire function, is the derivative of each of these pieces added together separately with proper signs. right? The derivative of a sum is the sum of the derivatives. Derivative is a linear operator. And so it goes through the sum and operates on every term in all of these, sums and, minus sums, but sums with a minus sign in front of them and so on. And so let's take them piece by piece. Let's do this first. So let's take that derivative. We are taking a derivative of log omega with respect to some specific n sub k. This is dd n sub k of the first term ni times log of the sum ni minus ni log ni. We're taking a derivative with respect to some specific n sub k. This runs over all the possible values of I. Somewhere in the sum there will be an n sub k. This is also running over all the possible microstate indices. And so somewhere there is an n57, n sub 57, or n sub k. First of all, when we look at this, so this guy is going to operate on this term, and it's going to operate on that term sequentially, right? Because the derivative of a sum, composite sum, or difference, is the sum or difference of the derivatives operated separately on them. Let's deal with the first term. We first recognize this as a product of two functions. The first function is what's in the first parentheses, sum over all ni. It's a perfectly valid function of many variables, where the function is just add the variables together. The second function that it's multiplying is log of the same thing. But just by virtue of the fact that we have a product of two functions, when we take a derivative, we have to use the product rule, right? So the product rule is the derivative of the first function times the second function plus the derivative of the second function times the first function. What does that look like? The derivative of the first function, sum of ni, you're taking a derivative of this function with respect to some n sub k. And so in the sum, there will be n1 plus n2 plus n3 plus n4 plus n5, right? This is n1 plus n2 plus blah, 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 blah. Somewhere in there, there's an n sub k plus n sub k plus 1, and so on. That's what this is. So n sub k will occur in only one place in the sum. All the other guys, n1 and all the other n sub k plus 1 and so on, are constants with respect to the variable n sub k. Because we're finding an unconstrained maximum now. And so there's only one n sub k in the sum. The derivative with respect to n sub k of all these guys is going to be 0. But when the derivative operator operates on the n sub k term, dd n sub k of n sub k, it's like ddx of x. It's just 1. And so this whole, of all this sum, the derivative operating on this sum gives you just 1. So the first term in the product rule is 1 multiplied by the first function, 1 multiplied by log of sum on I and I. Now we get the second result of the product rule, plus now the first function times the derivative of the second. The first function is the sum on I over ni. The derivative of the second. The derivative of a log of anything. So first of all, before we do that, this is a log of a function of a bunch of variables. So there is an inside function, just like that, and there's an outside function log. And when you have this inside-outside function, you of course use the chain rule from calculus. And so the chain rule here is the derivative of the log of this whole composite function with respect to this variable is 1 over the entire variable inside the log times by the chain rule times the derivative of the inside function with respect to the variable. And so the first thing we get here is 1 over what's inside the log times the derivative of the inside function. But the inside function here is the same as this. We already know what the derivative of a thing that looks like this is. ddnk of this thing finds a single nk and its derivative is 1. And so this is times 1. So we've dealt now with this term. We've used the product rule to differentiate with respect to some particular n sub k. Now we go on to this term. This term looks like n1 log n1 plus n2 log n2 plus blah, 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 n sub k log n sub k plus n sub k plus 1 times log of n sub k plus 1, blah, 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 and so on. And so once again, there will only be a single term in the sum that has n sub k in it. All the other derivatives of these guys with respect to n sub k are going to be 0 because they don't depend on n sub k. And so the only term that survives is n sub k times log n sub k. What is the derivative with respect to n sub k of n sub k times log n sub k? Once again, you have a product. A slightly more sane product, but a product of two functions, n sub k and log n sub k. The derivative of a product is the product rule, so it's the derivative of the first times the second. The derivative of the first, the derivative of n sub k with respect to n sub k is once again 1 times the second function, so log n sub k. So now remember, it comes in with a minus sign. Minus log n sub k and now minus the second version of the product rule. So the derivative of the second not the second version of the product rule, the second step in the product rule, the derivative of the first function, derivative of the second function times the first function. So the derivative of log of n sub k with respect to n sub k times n sub k. The derivative of log of n sub k is 1 over n sub k. There's no more inside function. Derivative of log of n sub k with respect to n sub k is 1 over n sub k. And so you get n sub k from the first function divided by n sub k. This thing, of course, that divided by that is, of course, going to give you 1. This is also going to give you 1. So this 1, this minus 1, is going to cancel this plus 1. So this term will undo that term. What will be left behind is log of sum over ni minus log of n sub k. That's the derivative of omega, of log of omega. So let me write this on top, I guess. So what we found is that ddn sub k of log of omega is equal to log of sum on I over ni minus log n sub k. Remember that the sum over ni is the total number of systems in the ensemble. So we can also write this as log of pi minus log of n sub k. Log of pi is a constant, whereas this value depends on n sub k. But remember that we needed to find the unconstrained extreme of L, the Lagrange function. So now we found the derivative of log of omega, but there are also those constraint terms. So we also have to find Let me now erase this. We also have to find ddn sub k of the first constraint, alpha sum on I and I. Well, this is alpha ddn sub k of sum on I and I. Remember, there's only one place where n sub k occurs in the sum. Its derivative is 1. So this thing is just alpha. ddn sub k, oops. The derivative with respect to n sub k of the second constraint, which was beta sum on I and I e sub I, is going to look something like this, but when the n sub k goes past the constant beta into the sum and operates on it, it encounters the one term n sub k times e sub k. The derivative with respect to n sub k is 1, but it's multiplied by the constant e sub k. And so here the answer is going to be beta e sub k. And so if we put all of this together, the derivative with respect to n sub k of the Lagrange function that we were finding the unconstrained maximum of is going to look like the bit from the log omega, which is log pi minus log n sub k, minus the derivative of the first constraint, minus alpha. Remember, it came in with a minus. Minus the derivative of the second constraint, minus beta e sub k. And this whole thing has to be set equal to 0 for all k equals 1, 2, and so on, for all the indices of every microstate. We can solve this now for n sub k. Solve for n sub k. And instead of just calling it n sub k, we're going to call it n sub k with the superscript star to indicate that this is that specific n sub k. This is that specific number of systems in the ensemble in microstate k that occurs when the dominant distribution takes place. And the reason why it's associated with the dominant distribution is because we said it corresponds to the maximal, constrained maximum of log of omega. And that's what we found. We found the constrained maximum of log of omega, or the unconstrained maximum of this modified Lagrange function. And so we have found that if we solve for n sub k star, what it equals is pi e to the minus alpha e to the minus beta e sub k. Where did this come from? I solve for log of n sub k. Let's say I put it on the right. I then have log of pi minus alpha minus beta e sub k. I then exponentiate both sides, so find the inverse of the log, or take the inverse of the log of both sides. Exponentiate both sides. Exponentiating log of n sub k on the right side gives you just n sub k, and we put a star index to remind us that this corresponds to the dominant distribution. On the left-hand side, you'll have left over log of pi minus alpha minus beta e sub k. You will be exponentiating that. Exponentiating this minus that is the product of those exponents. The first exponentiation of the log will just give you back pi. You get e to the minus alpha from an exponentiation of this term, and you get e to the minus beta e sub k from exponentiation of that term. So that's where we arrive here. If we rearrange this, this can be written as n sub k divided by pi equals e to the minus alpha e to the minus beta e sub k. Remember what this is. What we said was that given that one of our distributions absolutely dominates and is the only one that we effectively need to be concerned with, this is the probability to find our macroscopic system of interest in microstate K. This is the thing that we've been driving towards from the very beginning of this course so far. We said that as soon as we have this, we in principle have access to all the average values of all the relevant thermodynamic parameters of our macroscopic system of interest. In this case, a system that happens to have a constant n, constant v, and constant t. We know that that system can be found in very many microstates. We found that when we observe that one macroscopic system of interest with that number of particles, volume, and temperature fixed, we can find it in any one of its possible microstates with a probability p sub k. That probability p sub k is equal to some constant e to the minus alpha. Since alpha is a constant, this is also a constant e to the minus alpha, times a term that is not a constant, but actually depends on the microstate index k. How does it depend on the microstate index k? It depends on it through a decaying exponential e to the minus beta e sub k. So it depends on the second undetermined multiplier beta that we still have much to say about. But it also depends on the energy level, energy eigenvalue, that is associated with that microstate k. This is important to note that this is not the probability of observing your system in a specific energy level E sub k. It's the probability of observing your system in a specific microstate k. And of course, for every microstate, there is a specific energy. But remember that there are many degenerate microstates. If you have a bunch of different microstates, let's say from k to k plus 5, that were all degenerate, they would have the same probability of being observed because they all have the same energy. And what we found is that the probability for a system with a constant n, v, and t in the canonical ensemble, a system in contact with a thermal reservoir, the probability for it to be in any one of its microstates k is not the same for all microstates k. It depends on the energy of the microstate. And the larger the energy, the smaller the probability. Microstates that have large energies are less probable, less likely to be found at a given temperature, volume, and number of particles than microstates that have a smaller energy. So the largest probabilities are for the lower energy levels, or for the microstates that have the lower energy levels. And microstates that happen to have large energy levels will have relatively small probabilities, exponentially so. This is the Boltzmann distribution. We've now derived it. And in class, we have shown that e to the minus alpha must be a specific value if it is to be a normalized probability distribution. And working through the normalization condition, we found that e to the minus alpha was 1 divided by something called the partition function that we'll still have a lot more to say about. A lot more to say about. But nevertheless, this factor serves as a normalization kind of constant, normalization factor that makes the whole probability be a real probability distribution, where adding the probability for all the mutually exclusive exhaustive outcomes gives you 1, as they must. And of course, being in one microstate versus being in another microstate are mutually exclusive possibilities. And so this is a very powerful formula that we found that we're going to use in a number of ways. We're going to use the concept of the partition function for the duration of our thinking about statistical mechanics as applied to thermodynamics. But this here is the derivation using the Gibbs ensemble method of the probability to find our system of interest. We've now used the ensemble. We can, in a sense, set it aside. We are now again facing or looking at our one macroscopic system of interest that's sitting on our tabletop, whose average properties, whose thermodynamic properties we would like to be able to calculate from first principles from first principles, meaning that we have solved the Schrodinger equation for our system of interest in principle, right? And on a powerful enough computer, this can always be done to an extremely good degree of approximation. So we have the set of possible microstate indices, and we have their energy eigenvalues. And now that we have the energy eigenvalues, we will be able to calculate the probability that our system is found within a random observation at any one of its possible microstates. And with that probability distribution comes the power to calculate all the moments of the distribution, all the average properties. And we still have the burden to show how the average properties of the fluctuating variables like the energy and the pressure, as determined by the probability distribution, will ultimately give rise to the macroscopic thermodynamic measurements or thermodynamic properties that we learn about in chemical thermodynamics in Chem 163b. And about that, we will continue talking in our normal live Zoom lecture.